Or it seems semi-annual, so twice a year. You should come more often. School in geometry. This school begins with Christian Schnell, who will give a review of birational geometry. It's our own Christian Schnell from Stony Brook. Come here and see him also.
Okay. Okay, thanks very much. Yeah, so I guess the title is something like Overview of Birational Geometry, but of course I'm not going to give an overview of all of birational geometry, only certain very select topics. So I think what I'll do is I'll review some basic definitions and then some interesting results that might help you for the rest of the conference, like some things that you will see again in more detail during the conference. Okay, so let's start with the main definition. So let me take X to be a quasi-projective and irreducible variety. And this is over a field which I'll assume is algebraically closed. So K is an algebraically closed field. And so then the main definition is that we say that one of these varieties is birational to another variety. So write like this. And then there's a couple of different ways of saying this. So one would be to say that there's a rational map with a rational inverse. Right, this is the usual definition. So this rational map, it's not necessarily defined everywhere, but it's defined on sometimes open set, and then you ask it, there's an inverse map which is also rational. This is equivalent to saying that the two varieties have dense open sets that are isomorphic, right? So like here you just restrict to certain subsets where this phi and phi inverse give you isomorphisms. And you can also state this in terms of just field theory. So for each of these x's, since they are x and y, since they are irreducible, you have the field of rational functions. And this condition is equivalent to saying that the rational function fields are isomorphic. So these are the rational functions. As K algebras. Right? And then we'll also use one other definition. So this being birational is somehow the main relation that we're interested in, right? And it's kind of different from the relations you would find, say, in manifolds or things like that, because you're dealing with maps that are only defined on open sets as opposed to being defined everywhere. We'll use a somewhat weaker notion also. So we say that x and y are stably birational if they're birational up to projective spaces. So x times some projective space is birational to y times some other projective space. Okay. Okay, by the way, so since this is a mini school, if there are any questions at any point, please always feel free to ask, right? If I have my back turned at some point because I'm writing, then please just holler, okay? Okay, so what's the main example of some birational map? Something that's birational but not regular. Well, the main example are things like blowing ups, right? So let's look at that example a little bit. So the main example is blowing up. So let's consider a subvariety and say z and x are both non-singular. So this is closed, and they're both non-singular. And then we have this blowing up. So this is a new variety in which z gets replaced by a divisor. So the z may have some higher codimension, but in here you cut out the z and then replace it by a divisor. So this is let's call this maybe P. So the properties are that P is an isomorphism between x minus z and the blow up minus E, where E is a divisor now. Right. So this map is an isomorphism over the set x minus z, but it replaces the z by some higher dimensional subvariety, right? So locally, what does this look like? So if I have some open set U with local coordinates, say f1 up to fn. So on this x, I choose some local coordinates, like some regular functions in some neighborhood that give me local coordinates, and such that in this open set, z is defined by, say, the first r of these. And then the blow-up is locally, so then locally the blow-up is the subvariety of u times pr minus 1. So r is in this case is the codimension. And that's defined by these relations here, that the fi of x times the coordinates on projective space are proportional in this way, right, where the coordinates are x and like this. And so from this you see very clearly that if you're over the points of z, then all the f's are equal to 0, and then the fibers of this map are just the entire pr minus 1s. Whereas on the other points where not all the f's are 0, it's an isomorphism. And yeah, so globally, well, anyway, let's put up here. This is like the local picture, and globally, you cannot choose these functions that define z necessarily globally, and so then it's not just a product between x in the projective space, but there's a non-trivial bundle. So globally, this E is actually the projectivization of the normal bundle. So here the points are lines in the normal bundle, right? So so geometrically, what happens is, as everyone knows, that as you go on towards different points of z, these different directions get separated in the blow-up into the different points of the fiber, right? But so this is in any case, so this is a PR minus 1 bundle with fiber PR minus 1. Okay. So the blow-up is the most basic example of a rational map that is actually birational but doesn't have a regular inverse, right? Where the inverse is not defined everywhere. What makes the blow-up important is that it figures very prominently in many different results in birational geometry. So for example, you've probably heard about resolution of singularities. Like in the resolution of singularities theorem, it says that there's a procedure by which you can take a variety with singularities and turn it into a non-singular variety. And you do this by repeatedly blowing up smooth subvarieties like this. So this is one place in which this is important. Another one which will be important for the things that I'm going to describe is that, in fact, essentially every birational map can actually be understood in terms of blowing up, as a composition of blowing ups and blowing downs. So this is the so-called weak factorization theorem. So let me state this, maybe. This plays an important role in many results. This is the weak factorization theorem. So this is due to Abramovich, Karu, Matsuki, and Lodarczyk. And so this works in characteristic 0. So K is algebraically closed of characteristic 0. And then suppose we have a birational map Okay, so I don't put any dotted lines or something. I just say birational. So I mean, it's just, it may be an isomorphism, but maybe it's not an isomorphism. So then weak factorization says that there's a chain. So starting from x0, you can find a chain of rational maps that starts at x and ends at the variety y. And that gives a factorization of the phi that you start from. Right? And each of these individual maps into which you factor, either that map or the inverse of that map is a blowing up in a smooth subvariety. So such that each phi I or phi I inverse is a blowing up at a smooth subvariety.
Birational morphism or birational map?
Yeah, okay. So it's just a birational map.
I see.
Yeah, not necessarily a morphism, right? And so here also, these guys, for example, this phi naught, it may be just a blowing up, in which case it's actually a morphism, but it may be that it's actually the inverse of a blowing up, in which case it would not be a morphism, right? And like in the case of resolution of singularities, this thing is actually a little bit more precise. So this, for example, part of the statement is that you can choose these blowing ups and blowing downs in such a way that you don't modify the set where phi is already an isomorphism. You can do the blowing up in the set where actually phi or phi inverse are not defined. Okay, so the importance of this result is that it means that for many questions where you try to understand arbitrary birational maps, it's actually enough to just understand blowing up at smooth subvarieties because of this factorization. Okay, so I thought to show you one application of this result, I'll talk a bit about the so-called Motivic ring. This is a case where one can see this result in action. And then I go to the things that I'm really supposed to say. So the Motivic ring, or I sometimes call it the Grothendieck group of varieties. So, yeah.
In factorization theory, we do not assume that x over and y is smooth, right?
I don't think so. I mean, because you could sort of put in resolution of singularities if you wanted to, right? Which you could achieve by the same kind of.
Yeah, but then it will be not smooth, right? No?
Well, but I mean, I could. So I know over characteristic 0 also that x is birational to a non-singular variety, right?
Well, and the blowing up is a lot.
And I could,
centers.
yeah, and I could achieve the resolution also by blowing up at smooth centers. Yeah. Okay. So this Motivic ring is it's a place in which you can look at varieties and you can decompose varieties into pieces easily. Okay, so this is something where inside of this ring, it will make sense to say that if I write a variety as a closed subvariety plus the open complement, then the variety is actually in this ring the sum of the two pieces. Okay, and so the way this is achieved is just by defining it so that that happens. So this is just a quotient like this. So you take the free abelian group generated by classes of x, where x is a, say, k variety. Let's not be too precise about exactly what. And then this is modulo the following relations. So modulo the relations that identify X with a closed subvariety plus its complement. Okay, so this, well, with this definition, it's defined as a group, but there's actually an obvious product because you can multiply varieties, right? So this is a ring where the product is, if you define it on the generators, the product is just take the product of varieties over spec K. The unit element 1 is just the class of the point, right, which is the class of spec K. What's the 0 element in this ring? Yeah, the empty variety, that's right. Or I mean, in this, it's just the 0, the sum equals 0. But you can also think of it as being the empty set, right? And then there's one other important class that people always use that's called L, or the Lefschetz class. This is another name for the class of A1. Okay. So this ring may look very complicated, but I want to explain that one can actually understand it quite easily, or not easily, but it becomes a lot simpler and more manageable if you use, for example, the weak factorization theorem. So I want to tell you some results about this ring that can be done with weak factorization. Well, let's first observe a few small examples. So the first one is I can write the class of Pn in terms of L, right? If I use so if this is projective space, I can use the relations to write this as Pn minus 1 plus An, which is Pn minus 1 plus, and then this is the n, this is A1 n times, so this is just L to the n. Right, and so the upshot is that this is just, if I keep on doing, this is 1 plus L plus Ln. Another example would be, so in this ring, actually, things that are non-trivial as varieties may still be trivial as a class. So there are some identities that aren't quite apparent on the level of varieties itself. So for example, suppose I have a situation like this. I have a map, which is a fiber bundle. So this is a fiber bundle with fiber F in the Zariski topology. Okay, so X can be covered by open sets, by affine open sets, on which this map is actually just the product of X times F, but it may not be globally trivial. But because of being able to decompose X into pieces, this is actually, as a class, is just the same as the class of the product. Because I can just break up X into an open set where it's a product plus the complement, and I just keep on doing this. Then on each of these open sets, the thing is just the product, and then I just reassemble the pieces, and it's the same class as the product. Another example is blowing up. So this blowing up that we looked at earlier. So here I have Z, and here I have E. Because the map, so I can write X as the sum of the complement plus Z, and here also. And then on the complements, I have an isomorphism. So this tells me that in this Motivic ring, I have this identity here. And then I can understand E as a locally trivial PR minus 1 bundle. So this is actually the same as okay. So now, the first consequence of weak factorization is that one can actually simplify the definition of the Motivic ring quite a lot. So this is a somewhat older theorem by Bittner. So here again, you have to assume that the characteristic is 0, which is so that one can use resolution of singularities and also weak factorization. And then Bittner's theorem says that you have another presentation for this ring, namely it's the free abelian group on smooth projective varieties modulo, and then the only relations that you have to impose are the relations coming from blow up. Modulo the relations like this. Okay, so I'm not really going to explain the proof, but I mean, roughly speaking, the first thing that you have to do is you have to show that instead of using classes of arbitrary varieties, you can actually work with smooth projective varieties. And so that uses the fact that an arbitrary variety, an arbitrary, say, quasi-projective variety, can always be compactified into something projective, and then you can always resolve the singularities in characteristic 0. So this is why in the numerator it's enough to look at this smaller set, because the class of every variety can be written as some linear combination of classes of smooth projective things. And then, yeah. Oh, sorry.
What does a square bracket mean?
Ah.
The equivalence relation. Is it equivalence relations?
Yeah, I'm being, sorry, I was being a little bit sloppy. So I take the free abelian group generated by all projective varieties, right? So an element of that would be a sum a sub I, x sub I, where the x sub i's are varieties and the a sub i's are integers. And then I take the quotient by these relations, and I write bracket x for the class, really, for the equivalence class. Yeah, and so here I should technically erase the brackets, and I should just call the x the class in the ring. Yeah. Is it clear?
Well, I'm wondering what you do. So do you also mod out by isomorphism or something?
Yeah, you're right. Thanks. I mean, I guess it technically. No, it doesn't. Yeah, mod out by isomorphism. But maybe take the free abelian group on isomorphism classes of these things. Okay, are there other questions? All right. So the numerator is roughly resolution of singularities, and the denominator, by some procedure, follows from the weak factorization theorem. Okay, and then I wanted to tell you one other result about this, which is the relationship between this Motivic ring and actual birational geometry, or more precisely, stable birational geometry. So this is a very famous theorem by Larsen and Luntz. So what this says is that so what are the actual relations that we're looking at here, right, in this Motivic ring? So if we use this Bittner presentation, the relations are like this. You see that in this kind of relation, actually the left-hand side and the right-hand side are almost birational, right? Because this guy here, this is a smooth projective variety, which is birational to this one. And this product here is not quite birational to Z, but it's birational up to this PR minus 1 factor. So if I do, instead of looking at birational equivalence, I look at stable birational equivalence, where I ignore these factors, then the two sides are actually stably birational. And so Lars and Lunz proved in general that, again, assuming characteristic 0, that modulo the ideal generated by the class of the affine line, this is actually isomorphic to just something I'll write like this. So this is just the ring generated by this monoid called SB. So SB is the monoid of stable birational equivalence classes. So this is a product. This has a product by the stably birational class of x times the birational class of y is just that of the product. And the unit element is again just the class of a point, which is also the same as just the class of any Pn. Right? And so this isomorphism works by taking a class, the class of some x, to simply its stable birational isomorphism class. Right? And then you have to check that it preserves the relation. And this follows from what I said over here. Because by Bittner's theorem, the relations that you have to look at are like this. And here, this piece and this piece are stably birational. And this piece and this piece are stably birational. And then the main thing that one really has to show is that, in fact, the kernel is exactly generated by L. Right? So I mean, L goes to 0 because L is class of P1 minus the class of a point. But one can show that, in fact, anything that goes to 0 has to be a multiple of L. OK, so this says that this Motivic ring is basically keeping track of whether things are stably birational or not, except that there are some complications involving this class of L. If you forget about the complicated stuff introduced by L, then it's just stable birational equivalence. OK. Yeah, so that was the little excursion. OK, so now let me go back to special cases of being birational. Actually, the topic that will be of main interest for the conference is not just arbitrary birational maps, but it's whether or not something is birational to Pn, or just rational. So again, there's a couple of definitions that you will find. So the first one is x is called rational if it's birational to some Pn. Then there's various weakenings of it. So we already saw stably birational. So we can say it's stably rational if it's stably birational to Pn. So this means that x times some pk is birational to Pn. And then there's an even weaker notion called unirational. So it's unirational if it's dominated by something rational. In terms of fields, so the first condition is saying that if you look at the function field of x, it's purely transcendental, generated by just n independent variables, right? You can state this one by yourself if you like. And here this is saying that the function field, because this map is dominant, it means that the function field of x embeds into something purely transcendental. And so here the famous classical question is the so-called Derived problem, which asks, in terms of fields, whether this kind of condition always implies this condition. If you have a subfield of a purely transcendental field extension, is it actually itself purely transcendental? In terms of geometry, it's asking whether unirational and rational are equivalent, right? So I should say that I've ordered them by increasing, by implications, right? So if it's rational, then it's stably rational. If it's stably rational, then it's unirational. So the question is about going back in the opposite direction. Well, okay, so this Lurov problem, in low dimensions, the answer is yes, this is true. So the examples are, if you're looking at curves, in the case of curves, actually a curve, a smooth projective curve is rational exactly when the genus is 0. And in fact, all three conditions actually say that the genus of the curve has to be 0. Because in each of these cases, you can still calculate the genus and relate it to the genus of projective space, which is 0. So all three imply that. And so then actually X is not even birational too, but actually isomorphic to P1 if it's a smooth projective curve. So this depended on the fact that we have a very simple characterization of rationality in terms of this number, the genus. In dimension 2, for surfaces, there is still a numerical characterization of rationality. This is called Castelova's criterion. So it says that X is rational if and only if the irregularity and the second plurigenus are equal to 0. So this number Q, which is the dimension of the space of one forms, is equal to 0, and also this number P2, which is the space of sections of the second power of the canonical bundle. Again, this being purely numerical, you can actually relate these numbers. For example, if you have this dominant rational map here, you can actually relate these numbers on X to the numbers on Pn, and you can still show that something unirational is actually forced to be rational. So this implies that, so X unirational implies rational.
What are your assumptions on X right now?
Smooth projective, say. Yeah.
The field algebraically closed?
Yeah, the field algebraically closed. Yeah.
Was the arbitrary characteristic as well? I seem to remember there's some.
I suppose so, but maybe you have to, I don't know, maybe one has to exclude some low. I mean, I'm not an expert on non-zero characteristics, so.
True before that for it to work, because you consider the same question in terms of fields. For dimension 2 in characteristic P, you have to assume separability.
Okay.
I think.
For this field extension, you mean?
Yeah. Okay. For dimension 2. For dimension 1, it works fine.
Okay.
Okay.
All right. So in low dimension, these two things are equivalent, right? And there was a problem for quite a long time whether one can find counterexamples in higher dimensions. And so what people did is they looked at the next case, namely the three-dimensional case, and then roughly at the same time there were different people who found examples of threefolds that are unirational but not rational. So I want to explain what the strategy is, and then two different examples. One is by Artin and Mumford, but I'll just be very brief about that. And then there's a longer one by Clements and Griffiths that I'll explain in more detail. Disclosure, Griffiths is my grandfather, and Clements is my dad in terms of advisor relationship. So anyway, okay, so let's assume now that dimension X is equal to 3. So here, as I said, there are counterexamples. So to show that something is unirational, well, you have to produce this map. To show it's not rational, you have to find some kind of invariant that can distinguish rational and unirational things. And so what people use are, they look at the cohomology. And then there's two different things that can, in principle, so this gives two potential invariants. So one can show that if a threefold is unirational, its cohomology looks almost like that of a rational variety, except there's two places that are not quite controlled by the unirationality. The first one is if you look at the integral cohomology in degree 3. So now I guess I'm assuming that k is equal to c. So cohomology will mean the singular cohomology of the complex manifold. I guess there are some versions for different fields, but let me stick with this assumption. So the H3, you can look at the torsion part of it. And this is a potential, as I will explain, this is a potential way to distinguish between rational and unirational. And the second part is you can look at the Hodge theory or the Hodge structure on the third cohomology. And this leads to the so-called intermediate Jacobian. And so this first one is what Artin and Mumford did, and the second one is was introduced by Clements and Griffiths. OK, so what's the idea? So let's look at number 1 first. So I claim that this torsion subgroup of H3, this is actually a birational invariant. So if x and y are birational, then in fact the torsion subgroups of H3 are isomorphic. Well, so this might be hard to see in general, but if you know weak factorization, then it's actually very easy, because weak factorization says I only need to understand blowing up. So by weak factorization, I only need to consider blowing ups at smooth subvarieties. Now on a threefold, the only non-trivial things I can blow up would be points and non-singular curves, right? So I only need to look at blow-ups of points and blow-ups at non-singular curves. If I do the blow-up of a point, then what happens to the cohomology is that H2, well, let me call this x tilde, is the H2 of x plus a copy of z, which is the class of the exceptional divisor, and same for H4. And the H3 doesn't change. So H3 is the same. So in particular, the torsion subgroup doesn't change. When you blow up a curve, on the other hand, you do change the H3, but you don't add any torsion. So if I do so again, H2 and H4 change by a copy of z, and now H3 also changes. And you add a copy of the cohomology of the curve, but this piece here is torsion-free. OK, so again, you don't change the torsion part. And then by weak factorization, any birational map can be understood as a chain of such things. So I know that overall, the torsion part doesn't change. And so in particular, this implies that if x is rational, so if it's birational to P3, then the torsion part of the cohomology is the same as that of P3, which is 0. So the non-triviality of this is a way of showing that something is not rational, right? And so this, so Art and Mumford made these observations in their paper, and then they gave an example where this happened. So they looked at X, which is a branched covering of P3. So this is a 2-to-1 branched covering branched along a degree 4 surface. So I won't be very precise about this, but they write down some specific equations for degree 4 surfaces for which the covering has some special properties, and then they actually, I mean, I guess it's slightly singular, so probably they resolve the singularities, and then they actually managed to find non-trivial elements in the torsion subgroup. So then they show that this X is unirational by writing down equations, but the torsion part is non-zero. So it's not rational. Yeah?
How did they deduce that H3 torsion is not...
that is not trivial?
No, that is birational invariant. They didn't have weak factorization, right?
That's true, yeah. But I mean, it's also just on a threefold, right?
No.
So I think it's much easier to show that in that case. Okay. So sorry, I'm not going to say much about this example, but I will say in more detail how it looks like in the Clemens-Griffiths case. Any other questions? Yeah.
Apply technique too. We still also deduce that it's not.
No, I don't think so. Yeah, true. Okay, I mean, so yeah, sorry. So I'm taking the general approach that all of these stories will sort of continue during the conference. I mean, so many of these things have been developed further, and people during the conference will tell you how the story continues. Okay, so in particular, like the kind of comment that Jason made. Okay, so how about the second technique? So the second technique is to look at this intermediate Jacobian. So this is something Hodge theoretic. So again, I will assume that X is a threefold. So K is C, X a smooth projective threefold. So then the basic fact is that the cohomology of X has this Hodge decomposition. So this and not only do I have this decomposition, but of course I also have the intersection pairing on H3, because I can take two classes here and multiply them together. Then I get a six-dimensional form, and I can integrate that over X. Okay? And in fact, one also knows how the intersection pairing behaves on these different subspaces. And so the intermediate Jacobian is just, it's defined by analogy with the Jacobian of a curve, which is constructed from the H1 of a curve. So here you take the H3, but you do a similar construction. So you take the entire vector space, and you divide out by these two pieces here in the Hodge decomposition. And you also divide out by the integer cohomology. So this is, in other words, it's the H12 of X plus H03 of X. And the point is here you have the symmetry. So this left half has exactly the same dimension as the right half, which is, yeah. So if I kill half of it, then I just have a vector space of a certain dimension, and I'm dividing this by a lattice, by a Z module whose rank is exactly twice the dimension of the vector space. So this will actually be in general a torus, right? So this is a complex torus. So this was defined by Griffiths to study cycles. But then, so they observed that in the case, say when x is unirational, or more generally, suppose that the h30 is equal to 0, and also the h10 is equal to 0. So then in that case, this intermediate Jacobian is actually just this quotient here. And now the fact is that this is something that doesn't happen in general. So in general, you just get a torus. But in this special situation where you only have one subspace in the Hodge decomposition left, you actually can write down a polarization, and it actually becomes an abelian variety. So this is a principally polarized abelian variety. So i.e. it has an ample line bundle with one dimensional space of sections. Okay, how do you make it into an abelian variety? So there's a general criterion. So suppose you have something like this, a vector space modded out by a lattice. Then there's a criterion purely in terms of the lattice for whether or not it's an abelian variety. And this is taking the existence of an ample line bundle and just pulling it back to this vector space V and just looking at what kind of thing you get on the vector space, right? And so this is Riemann's criterion. So it says that a quotient like this is an abelian variety if and only if you have a Hermitian form on the vector space. So it's linear in the first argument, conjugate linear in the second one, who is such that the imaginary part is integer valued on gamma cross gamma. Okay, so roughly speaking, this imaginary part, you can think of this as a cohomology class. This is actually the first Chern class of the line bundle that you're trying to construct. And then the fact that this is Hermitian positive definite says that this first Chern class is actually positive as a form. And so then by translating the definitions back and forth, this actually ends up just giving you an ample line bundle, a positive line bundle. And in this cohomological case of the intermediate Jacobian, one can actually write this down. And this pairing is basically the intersection pairing on H3. So since we know so let me write this down briefly. So first of all, this map gamma into V in our case is just you take some gamma in, and then you write gamma as, so in the Hodge decomposition, it decomposes into these two pieces, which are conjugates to each other. And then you just map this to only the 1-2 part. Okay? And so then this H from V cross V to C is just, so the point is you basically just take the intersection pairing. So if I have two classes, you just basically take this integral over x, right? this is a 1-2 form, this is a 1-2 form. If I conjugate it, I get a 2-1 form, and so I can wedge them and integrate. And then I know from these so-called bilinear relations, I know the signs of this pairing on the different subspaces. And from that, you can figure out the kind of factor that you have to put in front to make it positive definite. Okay, so this comes from the bilinear relation. And then you check that. So you check that. If I apply this to some integral classes like this, so if I have gamma and delta and gamma, and I apply this to the 1-2 parts, then you can do the calculation. You see that because of the factor of 2, this is actually just it's just this. So it's just the usual intersection pairing on the integral cohomology. And then in particular, by Poincare duality, this is unimodular. So the pairing actually gives an isomorphism between the H3 with C coefficient and its dual. And so this means that this line bundle up there actually has just one section. And so that's why it's principally polarized. So this is unimodular. And so you get a principally polarized abelian variety. Okay. Now in this case, the situation is a little bit more complicated than for the torsion part. So it is not true that this intermediate Jacobian is a birational invariant. Right? Think about again what can happen. I could blow up points or curves on X in the threefold case. If I blow up a point, this will not change. But if I blow up a curve, it will change. In fact, it will change by adding a copy of the Jacobian of the curve. So the sort of thing that is a birational invariant is the question of whether or not this intermediate Jacobian is somehow computable from Jacobians of curves or not. So I'll say that more precisely in a moment. Okay, but so this is the sort of invariant that one gets here. Okay, now what Clemens and Griffiths did with this is they looked at another famous classical examples, which are cubic threefolds. So take some x in P4 as a non-singular cubic threefold. And then they showed that, so again, I guess I'm always, so K is C, right? Then X is unirational, but it's not rational. That's the thing they proved. Since I was very brief about the other example, let me actually give some more details in this case. Okay, just so how did they actually show this? So the unirationality, that is actually a classical. This is a classical result that was known long before them. And this is based on, this is just by an explicit geometric construction. And it uses the fact that X has lots of lines in it. Like any, a cubic surface has lines on it, a cubic threefold has lines. And as you increase the dimension, you get more and more lines on this thing. And in particular, here on this kind of X, you can do a dimension count. And there's a two-dimensional family of lines on this X. So we use the lines on X. So here's how this goes. So you fix one line. So fix a line so some awkward picture. So here's this line in X. So now let's suppose I take any point. So take any point. So for any point on this line, I can look at the tangent space. So the tangent space to X, but the projective tangent space. So this is a P3, right? So this is isomorphic to P3. And then I can look at lines in the tangent space that pass to this point x. So the set of lines such that x is contained in L. This is isomorphic to just the space of lines through a point in P3, so this is just a copy of P2. And overall, so for every point x on this line, I get a copy of P2. So as I vary the x, I get a P2 bundle over P1. So this gives me a P2 bundle. So again, for every point here, the fiber of this P2 bundle are just all the lines in the tangent space that go through that given point. Okay, so here's not very accurately is the tangent space to x at x. Obviously, this line L0 lies in the tangent space because it actually lies in x. And so I pick some point here, and then I look at other lines that go through that point, right? And now the observation is that this other line here, since it's in the tangent space at this point, it's tangent to x at this point. So the intersection between x and this line already has 2 points here. And because x has degree 3, it means that typically this line will intersect x in a unique third point. So unless L actually lies inside of x, this intersection is x union a third point that I'll call phi of xl. Okay? So that means, except when you unlock, well, except for like a small set of lines, namely all the lines that actually lie in x, typically I get a third intersection point. And so in this way, what you actually get is a rational map from B to x that takes such a pair, the point x and the line L, to this third intersection point.
There are 3 intersection points, right?
Yeah.
Can you actually make like a smooth family of these third points only? Because there will be another point on L intersect N. L intersect X, right?
Yeah, you can. I mean, you can make a smooth family assuming that you throw away those points where the line actually lies inside of x.
Okay.
I mean, so what you do is you restrict the equation for x, which is some cubic polynomial, to the equation for the line. And then you know it has a double root at the point x, and you just solve for the third root. And so you'll be able to write down some formulas for what this phi is in terms of coordinates. So now observe that this B is actually rational, right? Because again, if you write down the formulas, you throw away certain points on the line L0. It's actually a trivial P2 bundle. And so in particular, this B has an open set, which is just a product of an open set in P1 times P2. So it's a rational variety. And so here I'm mapping from a rational variety to x. So to show that x is unirational, just have to show that this map is dominant. Right? And in fact, we can see it's dominant of degree 2 in practice. Generic degree 2. So this is also just by a geometric argument. So let's say I fix some other point. Let's call it x prime in x, and then I ask how many points and lines are there, so that this third intersection point is that point x prime. Right? So how many? So in particular, this point x here has to lie on the line L, right? On the line L naught. So the easy way of doing this is look at the plane that's spanned by this line L naught and the point that you're interested in, right? You're looking for lines that join a point on the line L naught to this given point x prime here. So look at the plane that's spanned by them. That's a P2. And any line that we're interested in will have to lie in this P2. And now we're asking how many lines are there in this plane that go from here to here, but so that at the intersection point with L naught, this line is actually tangent to x. Right. Now here you observe that the intersection between x and this P2, this is, because x is degree 3, this is a cubic curve in P2. It contains this line, so this is actually a line union some conic. Again, generically. I mean, you may be unlucky, in which case it breaks up in some different way, but generically it will be a line together with some conic. And so then the 2 points that we're looking at are exactly just these two intersection points here. Right? So
Q need to pass through the x prime.
sorry?
Q need to pass through the plane.
Yeah. Thank you. Okay, I guess even if it's a schematic picture, it should be correct, right? Yes. Yeah. Okay, so then the lines that we're looking for are these lines that join x prime. They should stay inside the plane, right? It's these two lines, right? So phi inverse of x prime is, and the reason is that these two lines are actually tangent to x at these 2 points here, right? Because from this picture you see that the intersection between x and this P2 is singular exactly at these 2 points. And so any line that goes through this kind of singular point here will actually be tangent to x at those points. But if I go through one of these smooth points here, then it will not be tangent. And so in any case, so the upshot is that x is unirational. Because you have this 2-to-1 map from something rational. Okay. So now, how did they show that it's not rational? So well, suppose it was, right? So then this would mean that there would be a birational map between x and P3. By weak factorization, I can again understand this map as a composition of blowing up set points and blowing up set smooth curves. So by weak factorization, this is a chain of blowing up at points and blowing up at curves. And so this does not change H3, hence J3. And the blowing up of a curve, H3 of the blow up is H3 of x plus a copy of H1 of the curve. And then what actually happens to the intermediate Jacobian is the intermediate Jacobian of the blow up is the original intermediate Jacobian times the Jacobian of the curve. Because when you construct this torus that I wrote from the H1 of a curve, you just get the Jacobian of the curve. And so you see from this, by weak factorization, that if x was rational, then its intermediate Jacobian would be expressible in terms of Jacobians of curves in the following sense, that so x rational would imply that you would have something like this, right? Where the curves may be either on this side or that side, depending on whether in the weak factorization, the map is a blow-up or the inverse of the blow-up. Right? So that you get curves on both sides. Now in our case, so in the cubic threefold case, this J3 of x is a principally polarized abelian variety of dimension 5. Because you can write down actually what all the Hodge numbers of x are. So H1, H2. So here's the table of Hodge numbers. Okay, so this is the H3. So this one can calculate because one can calculate the Hodge structures for any hypersurface in projective space by some method by Griffiths. And so you find that this number is 5. So it's a 5-dimensional variety. And now the observation is that if you had this decomposition, in fact, this would imply that actually the Jacobian of x, the intermediate Jacobian of x has to be isomorphic to just one of these curves. So where Ci is a smooth projective curve of genus 5. Okay, so it does, I mean, this is not completely apparent from this decomposition, right? At first, from weak factorization, I just get this kind of decomposition with curves on both sides. But the point is, these principally polarized abelian varieties, they actually have unique decomposition into irreducible things. Whether or not something breaks up into a product or not can be detected by looking at the theta divisor, which is the section of this unique section of this ample line bundle, the zero set of this unique section of this ample line bundle. In the case of the cubic threefold, one shows geometrically that this theta divisor is irreducible, and it's also irreducible on these on the Jacobian of the curves. So in fact, all of these pieces are irreducible as principally polarized abelian varieties. And then this kind of decomposition means that actually the factors have to match up. And so in particular, this guy has to match up with one of the factors on this side here. And so then the way Clemens and Griffiths showed irrationality is just by finding some way of distinguishing the intermediate Jacobian of x from the intermediate Jacobian of a curve. And so Clemens Griffiths again, they showed that J3 of x is not isomorphic to J of a curve, and by looking at the singularities, roughly speaking. Of the theta divisors. So one can understand geometrically what this this divisor here, the section of this ample line bundle, actually is. And so it turns out that the theta divisor on the cubic threefold, this has a unique singular point. Right, so in particular, the singular locus is just a single point. But one knows classically that the theta divisor on a curve has singular locus at least dimension 1. Depending on whether or not the curve is hyperelliptic. Okay, and so the singularities distinguish between these two cases, and so in particular, they cannot be isomorphic. So then this shows it's not rational. Okay. Again, you'll see during the conference that these two methods are sort of the germs for more recent development. So both of them have kind of been developed in different directions, both the torsion part and this intermediate Jacobian business end. Okay. Let's see, what's the organizers? Shall I stop at 15 or shall I go until maybe 20 or 20 is fine? Okay. I have a little bit more to say, so are there questions? All right. So then let's briefly talk about another topic. So far everything was basically in terms of blowing up. But there's other kinds of birational mappings that are of interest, especially for the so-called minimal model program. And these are so-called flips and flops. So I thought I would finish by briefly saying something about those. So these are birational maps that different from a blow-up that only happen in codimension 2 or bigger. Okay, so the blow-up, you take something of codimension 2 or bigger, but then you replace it by a divisor. In the flips and flops, the difference is that you don't introduce any divisors. You take something of codimension 2 or bigger, you remove it, but then the thing that you put in is again codimension 2 or bigger. So here I will not be all that general, but I will just give an example or a few examples. This is the so-called standard flip or flop, depending on. So flips and flops, they're almost the same, except, well, anyway, you'll see. So a flop is a flip with a special property. So the standard flip is like this. Suppose I have a smooth projective variety X, and suppose it contains a subvariety isomorphic to pk. So this is smooth, say, and this is a closed subvariety. And let's suppose that this situation is very special, so that the normal bundle is actually just O of -1 to some power, say, L plus 1. So here k plus L plus 1 is the dimension of X, right? So if I have this, I can blow up this subvariety, and it gets replaced by a divisor, right? So I can look up. Let's call this X tilde. So this has an exceptional divisor, which is where it's the projectivization of the normal bundle. This is basically a trivial bundle. This is just the product of pk and pl. And the line bundle of the divisor, so the normal bundle of this E, is -1, -1. So it's -1 in both the original directions that I blew up and in the new directions. And so now here the situation looks kind of symmetric in the k and l, right? Because I have -1 in both arguments. So then sometimes it happens that inside of this X tilde you can actually, which we got by blowing up and introducing this PL, sometimes it happens that you can actually contract this original PK and still get a projective variety. So suppose, this doesn't always happen, but sometimes, suppose that we can contract the pk direction to get some x prime. So then if this is possible, then this x prime will contain a copy of pl, and the blow up at this pl of x prime will be again isomorphic to x tilde, right? So schematically, it's like this. So here's the x tilde, and it maps down to x and x prime. And here, we're blowing up the pk, and here we're blowing up the pl. OK. So now what is actually different on these two sides, right? So what we're basically doing is we're taking out this pk and we're replacing it by this pl. What I claim that what's different is this pk sits inside of x in a different way with respect to the canonical bundle. So you can use a junction to actually calculate what the canonical bundle is on this pk. So it says the canonical bundle of X restricted to pk times the determinant of the normal bundle is the omega of pk, which is O of minus k minus 1. The determinant of the normal bundle is O of minus L minus 1. And so the conclusion is that omega x on pk is O of L minus k. And then similarly, the other one, it's just the role of k and L got swapped. Okay, so if k is bigger than L, then this is an example of a flip. Right? So what happened is we had a subvariety pk on which the canonical bundle was negative. We took it out, replaced it by a PL, and on this PL, the canonical bundle is now positive. Right? So this is a typical step in this minimal model program that you've probably heard of. So the minimal model program aims to take a variety and get rid of all.
What if you just go back in the other direction?
Then it's not a flip. Then you take a negative subvariety and make it positive and make it negative.
Isn't it that the omega of the subvariety is omega of the big one tensor, the determinant? I think you got the sign wrong.
Yeah. The omega of the subvariety, which is pk, is the omega of the big one times the determinant of the
think of a P1 sitting inside of a K3 surface. So omega of the big one is trivial. Omega of the curve and the determinant of the normal bundle are both negative.
The normal bundle, that's in dual.
That's in dual.
You just change your signs.
This is a Mukai flop. It's not a flip.
Which sign do I need to change?
Just omega x is omega p tensor, then the det n comes on the other side.
Okay.
Just change your minus L minus 1 to plus.
But then do the signs still work out? The normal bundle is minus 1, right?
This is an example of a Mukai flop, I believe.
But I mean, your example doesn't work for this, right? Because I'm assuming that k plus L is the...
If k equals L, I'm sorry, it's a Mukai flop.
I think you're just going in the other direction. You're going from positive to,
Yeah, so this, if k is bigger than L, there's a preferred direction in that on one side it's negative, on the other side it's positive.
The question is what is normal bundle for PL, right? So for PK we know the normal bundle.
So for the PL will be the same one, but just O minus 1 to the power k plus 1.
You've just got, the signs are just back. Just go from the L to the K instead of the K to the L.
Then I don't see how the numbers work. Okay, sorry, so what's the objection? So the objection is to have the determinant of the normal bundle here.
Should be the determinant of the normal bundle dual.
On this side, right?
The determinant of normal one.
But I mean, in the case of a divisor, it's the canonical bundle of the divisor is D is kx plus D restricted to D, right? So it's k plus the normal bundle restricted to the...
No, it's omega.
Okay, sorry. So yeah, so we'll hopefully straighten it out. But I think this is actually right in terms of the numbers. Okay, so as I was saying, it's a typical step in a minimal model program in that you've taken a subvariety on which k, the canonical bundle was negative, you replaced it by a subvariety on which it became positive, right? And the case when k is equal to L, this is an example of a flop, because in this case, the omega x is trivial.
He's right. Yeah, he's right. Oh, x is the bigger one. Yeah, that's we're just getting confused what's big and what's small.
Okay, so here, if k is equal to L, I take out a pk and I put in another pk, but I don't change the So in both cases, the canonical bundle is actually trivial on that. And this is the kind of operation that happens among minimal models. So this is a change. So in this minimal model program, you do these kind of steps to eliminate subvarieties on which the canonical bundle is negative. And then after you arrived at a situation where you got rid of all of these, you still have the possibility of going among different minimal models by making this kind of replacement here, by taking some subvariety and kind of re-embedding it in a slightly different way, or flopping it. That keeps the positivity of the canonical bundle unchanged, but slightly changes the variety. Okay, so in this corner, I will just squeeze the last example. So a typical example would be, I have an ODP singularity on a threefold, dimension 3. I can look at the whole blow-up, which has exceptional divisor P1 cross P1. And then sometimes, if I'm lucky, with normal bundle O of -1, O of -1. If I'm lucky, sometimes then I can contract either one of these two rulings in the category of projective varieties, and I produce two different varieties here, where here I contract one of the rulings and I leave only a P1, and here I contract the other ruling and I leave a P1. Okay, this is an example of that for K and L equals 1 and dimension 3. And there you see why it's called a flop, because it takes a line in this a P1 in this orientation and it kind of flops it to the other orientation. Okay, sorry, then I guess I'll stop here. Thank you.
Any further questions for Christian? Okay, I'm Christian again.
Okay.
So the next talk,